Imagine a world where communication has no boundaries, where a simple hand gesture can instantly turn into meaningful text. That's the power of machine learning we are exploring today. Welcome to this ML project, a real time sign language to text conversion web app powered by machine learning, computer vision, and deep learning. A few months ago, I came across a video of a deaf person struggling to communicate even basic needs because others could not understand sign language. That moment stuck with me. What if technology could bridge the gap? What if a camera could see gestures and translate them into words all in real time? That simple thought sparked this ML project. So, I decided to build a sign language translator ML web app, something that could take hand gestures, images, videos, or even live webcam feed and instantly translate them into readable text using AI. Under the hood, it's powered by Flask for the backend, TensorFlow and Keras for gesture recognition, and MediaPipe and OpenCV for ML-based hand tracking and image processing. The web app offers two interactive modes. Upload mode uploads hand gesture images or short videos for instant translation. Live mode uses webcam for real-time ML-based gesture recognition. It's not just a demo, it is a step towards inclusive communication using ML technology. The model has been trained on diverse hand gestures datasets pre-processed with OpenCV, and predictions are handled frame by frame for smooth video translation. The front end, a clean minimal HTML, CSS and JavaScript interface allowing users to switch seamlessly between upload and live camera modes. And to make this ML project scalable and deployable anywhere, I have Dockerized the entire application so it runs smoothly on any system without dependency errors or setup issues. When I first built this Flask based ML app, it worked perfectly on my system. But when I tried running it on another laptop, I faced dependency errors, TensorFlow mismatch, and OpenCV version conflicts. That's when I realized the importance of Docker for ML projects. Docker allows us to package the entire ML project, code, environment, and dependencies into a single container image. This ensures the same ML model, Flask app, and libraries run identically across all systems. So I created a Docker file for this project. It starts from a lightweight Python base image, Python 3.11 Slim. Install all required ML libraries like TensorFlow, MediaPipe, Flask, and OpenCV, and copies the source files into a self-contained environment. Finally, with GunRecon, I installed the MS Flask app into production mode on port 5000. To simplify management, I also built a Docker compose.yaml file. It maps ports, preserves uploaded files, and lets us deploy anywhere using a single command. Docker compose up d build. Within seconds, the entire ML app runs. No work on my machine issues anymore. Learning Docker taught me how to deploy ML models efficiently while ensuring reproducibility and scalability, two essential skills for every ML engineer. Docker isn't just about a DevOps tool, it is the bridge between machine learning experiments and real world deployment. Open app.py and write the following code. Step 1, importing libraries. Import OS, import CV2, import NumPy as NP, import MediaPipe as MP. OS helps to work with folders and files. CV2, OpenCV used for image and video processing. NumPy handles arrays and math operations. MediaPipe detects hand in images and videos. From Flask, import Flask, request, JSONify, render template, response. From Keras.model, import sequential load model. From Keras.layers, import conv2 max polling 2D, flatten, dense, dropout. From TensorFlow.Keras preprocessing.image, import image data generator. From Rexarch.utilities, import secure file name. Flask helps in creating a web app so we can upload images, videos, or use live webcam. Keras builds and loads the deep learning model. Image data generator arguments image for training. And secure file ensures uploaded files have safe names. Import warnings. Warnings.filter warnings ignored. Warnings helps hide unnecessary warning messages. Step 2. Configuration. Data dir equals to data, image size equal to 224, model path equals to modelnet model.h5, uploaded folder equals to uploads, allowed extensions equal to mp4, avi, mov, mkv, jpg, jpeg and png. Labels equal to sorted, os.list dir, data dir. Data dir helps in folder containing training images. Image size, all images resized to 224 into 224 pixels for the model. Model path, file where trained model will be saved. Uploaded folder, folder to store uploaded images and videos. Allowed extensions, allow only these files to be uploaded. Labels, reads all subfolders in data as class labels like A, B, C for sign language letters. Step 3. Flask App Setup. App equals to Flask name, app.configuration, upload folder equals to upload folder, os dot make dirs upload folder, comma exist ok equal to true. Creates the Flask app, sets the upload folder, os dot mark dirs exist ok equals to true, creates the folder if it does not exist. Step 4. MediaPipe hand detection setup. MP hands equal to mp.solutions.hand, mp drawing equals to mp.solutions.drawing utilities, mp drawing style equals to mp.solutions.drawing style. hand detector equals to mp hands dot hands, static image mode equals to false, max num hands equal to 1, mean detection confidence 0.5, and mean tracking confidence 0.5. MP hands loads the hand detection module. MP drawing draws the landmarks on the hands. MP detector detects one hand at a time with medium confidence. Step 5. Build and train model. Def build and train model. DataGen equals to image data generator. Rescale 1 by 255, validation split equals to zero point 0.2. Image data generator normalizes the images and splits them into 80% training and 20% for validation. Train gen equals to datagen dot flow from directory. Data dir target size equal to image size, image size. Batch size equals to 32. Class mode equals to categorical. Subset equals to training. Validation gen equals to datagen dot flow from directory. Data dir target size, image size. Batch size equals to 32. Class mode equals to categorical. Subset equals to validation. Loads the images from folders, converts label into one hot encoding categorical. Labels equals to list, train gen dot class indices dot keys, updates label with the class names. Model equals to sequential, conf 2d 32, 3, 3, activation equals to relu, input size, image size equal to 3, max polling 2D 2, 2, conf 2D 64 3, 3 activation equals to relu, max polling 2D 2, 2, conf 2D 128, 3, 3 activation equals to relu, max polling 2D 2, 2, flatten dense 128, activation equals to relu, dropout 0.5, dense length levels, activation equals to softmax. Builds a convolutional neural network. Conv2D detects features from the images. Max polling 2D reduces image size to save computation. Flatten converts the 2D features to 1D for dense layers. Dense equals to fully connects the layers and dropout avoids overfitting. Softmax predicts probability of each class. Model.compile optimizer equals to Adam, loss equals to categorical cross entropy, matrix equals to accuracy, model.fit train gen epos equals to 20, and validation data equals to validation gen. Model.save model path compiles, trains, and saves the model. Step 6. Load and train model. If os.path.exist model path model equals to load model model path, print loaded pre-trained model net model, else print model not found. Starting training. Model equals to build and train model. If a trained model exists, load it, otherwise train a new model. Step 7. Helper functions. Def allowed file name, return in file name and file name dot rsplit, lower in allowed extensions. Check if uploaded file is allowed. Def detect and crop hand frames. Image RGB equals to cv2 dot cvt color frame, comma cv2 dot color bgr to RGB. Results equals to hand detector dot process image RGB. Converts the image to RGB for MediaPipe. Detects hand. If not, results dot multi-hand landmarks return none. Returns nothing if no hand detected. Cropped equals to frame y min y max x min x max. Return cropped. Crops only the hand from the frame. Def process frame image equals to cv2 dot resize frame comma image size comma image equals to image dot as type float 32 by 255 image equals to np dot expand dimensions image axis equals to 0 return image resizes normalizes and add batch dimensions for model input. Def predict frame cropped equals to detect and cropped hand frame. If cropped is none, return no hands detected. Processed equals to process frame cropped. Predict equals to model dot predict. Processed verbose equals to 0. Class index equals to mp dot aggregation max prediction. Confidence equals to float. np dot max predict. Return labels class index comma confidence. Detects hand, preprocess it, and predicts classes. Returns label and confidence. Step 8. Video prediction. Def extract frames and predict video path, comma step equals to 5, cap equals to CV2 dot video capture video path collapsed for character in sequence if not collapsed or character not equals to collapsed minus 1 collapsed dot append character return join collapsed reads the video every step frames predict each frame avoids duplicate consecutive predictions returns final prediction as a sequence. Step 9. Flask routes. App.root def index return render template index.html loads the home page at the rate app.root predict image methods equal to post def predict image return jsonify prediction label comma confidence equals to conf uploads the image return prediction and confidence app.root predict video methods equal to post def predict video return jsonify prediction sequence uploads a video returns a predicted sequence. Step 10. Live webcam. Def generate frames. Cap equals to CV2 dot video capture 0 while true. Success, comma frame equals to cap dot read. Label conf equals to predict frame. Display text equals to f label conf to f if label not no hands detected else label. CV2 dot put text frame comma display text 10 comma 30. CV2 dot font Hershey simplex 1 comma 0255 comma 0 comma 2. Red buffer equals to CV2 dot image code jpg dot frame. Frame bytes equal to buffer dot 2 bytes yield plus frame bytes. Captures the live webcam feed, predicts each frame, adds label text, streams it to the browser. At the rate app dot root predict live, dev predict live, return responses, generate frames, mine type equals to multipart x mixed replace boundary equals to frame. Routes to show live webcam prediction. Main function. Step 11 is the main function. If name equals to main, app.return app.run debug equals to true. Starts the Flask app in debug mode. Auto reloads on code changes. So what really happens in the code is that it detects the hands, predicts sign using CNNs, and works on images, videos, and live webcams. Uses MediaPipe for hand detection and Keras for model prediction. Flask makes it interactive and web accessible. The flowchart would be input, image, video, live webcam, hand detection using MediaPipe, crop the hand region from frame, preprocess image for CNN model, predict sign using Keras CNN model, output equals to predict label. We have just built an amazing AI-powered sign language translator using Flask, TensorFlow, and OpenCV. It can take a video or live webcam feed, analyzes hand gestures, and instantly translate them into text. But there's one big problem. Your app only runs properly on your system. Every time someone else tries to run it, dependencies break, TensorFlow crashes, or the Flask server won't start. That's where Docker comes to rescue. In today's video, we are going to containerize our sign language translator, turning this full AI project into a portable, production ready application that runs anywhere on Windows, Mac, or even a cloud server with just a single command. We'll start by writing a Docker file from scratch to package everything Flask, TensorFlow, Keras, NumPy, and OpenCV inside a lightweight Python environment. Then we'll create a Docker Compose setup to manage our web service uploads model file automatically. By the end, you will be able to run this entire project using Docker Compose Up build, and instantly you will see a translator live at localhost 5000. No manual installs, no dependencies issues, just clean, reproducible AI magic. Step 1, understanding the folder structure. Before we jump into Docker, let's look at how our project is structured. Here's what our sign language translator folder looks like. App.py is our Flask backend. It loads our trained model and handles prediction. Templates folder contains index.html, which contains the front-end layout for uploading videos or using the webcam. The static folder contains the script.js, which manages the live video streaming and API calls. Static folder contains script.js, which gives it that clean and modern look. ModelNet model.h5 is our pre-trained model file. And finally, uploads is where our uploaded media will be stored. This structure helps our web app modular, simple, and ready for deployment. Step 2, setting up requirements.txt. Next up, let's tell Docker exactly what dependencies our project needs. Create a new file called requirements.txt inside the project folder and add the following lines. Flask version 3.0.3, OpenCV Python headless 4.10.0.84 version. Similarly, TensorFlow versions, Keras version, NumPy, and Conrecon. Now you notice that we are using OpenCV Python headless instead of normal OpenCV. Why? Because Docker containers don't have a graphical interface, so we don't need GUI based OpenCV packages. This makes our image smaller, faster, and cleaner. Conrecon is also added here. It is a lightweight production ready server for Flask apps. We'll use that instead of the default Flask development server. Step 3, writing the Docker file. Now comes the fun part, creating our Docker file. This is the blueprint that tells Docker how to build and run our app. Use the official Python image from Python 3.11 Slim. Set the working directory, work directory app, install system dependencies for OpenCV, and then copy the project files. Install dependencies, expose the Flask server to 5000 port, and start the Flask app using Gunrecon for production. We start with the simple Python.11 3.11 Slim base image. It's a lightweight and fast. We set our working directory to app, then we install system level dependencies needed by OpenCV. Next, we copy all our project files into the container. We install our Python packages listed in our requirements.txt. We expose our port to 5000. That's where Flask runs. And finally, we start our Flask app using Gunrecon, which will handle production traffic efficiently. Step 4, adding the Docker Compose. Now, to make things even easier, let's add a Docker Compose.yaml file. This will let us build, run, and manage our app with a single command. Version 3.9 services web build container image sign language translator, the name of the file, port 5000, volumes, apps, uploads, environment, flash new environment, restart always. This configuration defines our service, our web app. It builds from our Docker file, maps our local port to 5000 to the container port 5000, mounts our project directory so changes are reflected instantly, and ensures our uploads and model file persist even after restart. Step 5, build and run your container. Now that everything is set up, let's build our Docker image. Open your terminal in the project folder and run docker build t sign language translator. Docker will start building the image, installing dependencies, copying files, and preparing your environment. Once it's done, run your app with docker run p 5000 sign language translator. Now open your browser and go to http localhost 5000 and boom, your sign language translator app is running completely inside a Docker container. No setup issues, no dependency errors, just smooth portable AI magic.